Okay, should be good. Okay, so here it goes, guys. Ready? Okay, shh. Up here. Okay. So, we have the following situation. Suppose we have an inverted cone, okay, and that's a tank, okay, and you got water inside the cone that's leaking out from a hole in the bottom, like that, okay? Now, let's think about that. The first thing I want you to notice is, doesn't the water itself also form a cone, doesn't it? Okay, and so what's changing here? John, can you move back a little bit there, or what you can't see, or what? Okay, okay. And so what's changing as that water leaks out, guys? Think about what's changing. Isn't the radius of water going to change? Isn't the height of the water going to change? And isn't the volume of the water also going to change? All three of those variables are going to change, right? V, R, and H are all changing over time as this takes place. Everybody with me on that? So that's the way you have to start thinking. Okay, what's changing over time and what's not changing over time? Okay, so in this case, all three of those are changing. And so we want to now talk about the rate at which those are changing as time passes. Okay, and so clearly, if I write dV over dt, that represents what? The rate at which the volume of water is changing over time. That represents what? The rate at which the radius is changing over time, and clearly that represents the rate at which the height of the water is changing over time. Okay, so get used to writing those rates like that with respect to time. Okay, now, what we now want to do is we now want to somehow get those in an equation. And so to do that, what you have to do is start with the diagram and think about it. Okay, and so what would we come up with here is an equation that relates V, H, and R. So what equation for this situation would relate V, H, and R? Well, it's simple. You got to go back to geometry and get this formula. Isn't that the volume for a cone? Isn't it? Everybody remember that? And again, if you don't remember that, I will give it to you. So anyway. Okay, now what I want to do is I want to somehow get these three rates in there. So how can I get these three rates in there? Well, what you're going to have to do is you're going to have to differentiate both sides with respect to what? T. Isn't that the only way you're going to get those rates in there? Is if you differentiate both sides of this volume equation with respect to T. So here it goes. Ready? What's the derivative of V? Well, it's 1, but then you got to multiply by what? dV over dt, because you're differentiating with respect to T, not V. Remember, every time you differentiate with respect to a different variable, you got to put d something, Remember that? Okay? All right, now what about here? Well, this side you got to treat like a product, don't you? Because R and H are both variables, so don't you have to use the product rule? So that's what I did. I took the derivative of that, which I get just by bringing down the 2 and subtracting 1 from the exponent. Okay? And then don't I got to multiply by dr dt, guys, don't I? So again, this is a derivative of that. And then times the second function. And then plus the first function. Again, this is just the product rule. So plus the first function, which is that. And now times the derivative of the second. And so what's the derivative of h, guys? Well, 1, but then I got to put a what? dH over dt. Okay, everybody with me on that? And now, by the way, if I simplify it, I get to here. And so what is this? That is an equation that relates what? The rate of change of the volume with the rate of change of the radius with the rate of change of the height. Okay? And so guess what the section is called then? Guess what the section is called? Related rates. That's what we're doing, right? We're writing equations that relate the rates between quantities that are changing over time. Does that make sense? Okay? All right. Now, by the way, just a couple quick observations that are important for you to start thinking about. As the water leaks out, yeah, everything's changing, but what's getting bigger, what's getting smaller? Is the radius getting smaller or bigger? Smaller. So you would expect a negative rate of change, wouldn't you, for R? Is the height of the water getting smaller or bigger? Smaller. right? So h is decreasing, so you'd, again, expect a negative rate of change for dH dt. What about the volume? Is the volume increasing or decreasing? Decreasing. So again, you would expect a negative rate of change for the volume as well, wouldn't you? That's very important, because getting just the sign wrong will give you a wrong answer. So it's very important that you start thinking about whether these quantities are increasing or decreasing over time, so that you know whether to make the rate of change positive or negative. Is that clear? Very important that you think about that. Okay, so that's just an introduction of what we're doing today. And now here's what we're going to do then in all the problems in the next couple examples, and as well as on all your homework problems tonight. This is how you're going to approach every problem from start to finish. Are you ready? First thing I want you to do is draw a diagram like I did. Didn't I draw a diagram to kind of picture what was happening? Okay, draw a diagram, and also make sure you assign variables to things that can change. Okay? And then anything that's a constant you can label as a constant right at the beginning of your drawing. Is that clear? Okay, then from there, what I want you to do is write down what rates you are given and what rates you're trying to find and when. Very important, like I just said. I just said this a minute ago. If a quantity is increasing, make sure the rate of change is what? Positive. If the quantity is decreasing, make sure the rate of change is negative. All right, next step. You then want to come up with an equation that relates all the variables and the constants in what you're given and what you're trying to find. Kind of like I did here, right? Didn't I come up with that equation from geometry, right? Okay, after that, you want to differentiate both sides of the equation with respect to t. Isn't that the only way you're going to get those rates in there? Agreed? And then at the end, this is how you finish. At that point, after you've set up the equation and differentiated with respect to t, you can go ahead and substitute in all given values and solve for the rate you are trying to find. Now again, I'll talk about more about this in a minute, but just make a note here that you sometimes need to momentarily freeze all quantities in your diagram in order to calculate any missing values. And that's only at the end. Okay, so I'm going to write that as an important note here. You may not substitute in a value for a variable if it's changing over time until after you've what? Until after you've differentiated. That's the number one mistake you're going to make right there. You're going to put in a value for a variable too soon, and then you're going to get the incorrect rate that you're looking for. Do not make that mistake. All right, it'll make more sense when I do some examples. So here we go. Ready? Again, these are all typed up for you. You don't have to write anything down. All I ask you is that you stay awake and pay attention. Okay? Here you go. Okay, so this is what a problem might look like on your homework tonight or on the test next week. Okay, they're all going to be application problems. Okay, so it says air is pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second, right? Okay, by the way, everybody take a look at that right now. I told you that that's the rate at which the volume's increasing. But suppose I didn't. Suppose I didn't tell you that. Well, in that case, I want you to look at the units. What are the units? Cubic centimeters over what? Seconds. So even if I don't tell you what that is, can't you just look at the units and figure it out? What is cubic centimeters? That's a unit of what? Volume. What's seconds? It's a unit of time, right? And so just by looking at the units, you can tell me that that's what? dV over dt. Is that clear? It's a change in volume over change in time. So again, so what I want you to do is I want you to read that first sentence and write down that that tells you it's what? That's what? dV dt is 100. Now, how do I know it's positive and not negative 100? Because it's increasing at that rate. If it said decreases at that rate, you would have put a what there? A negative. Are you catching this? This is very important. Okay? All right, then it goes on to say, how fast is the radius of the balloon changing? So what that means is what? That means we want to find what? dr over dt. Understand? And so I actually want you to write it like this. Just kind of like you did in geometry with your proofs. Always write down what you're given. We're given dV dt, which is how fast the volume is changing. You want to find dr dt, which is how fast is the radius is changing. Now you want to find dr dt at the moment in time when what? When the radius is what? 20. So you're trying to find dr when R is 20. So you got to write all that down. Without that, you're not going to know what to do next. So I want to see that on everybody's paper when I'm checking your homework. Is that clear? Okay? All right, now, from there, this is what you focus on. Okay, you focus on what the variables are. What are the variables? V and what? What are the variables in your given and find? What are they? V and R. So you got to write an equation for a sphere, right? Isn't the balloon the shape of a sphere? So you got to write a formula for a sphere that relates V and what? R. Well, go back to geometry. Isn't that the volume for a sphere from geometry, isn't it? V equals 4/3 pi r cubed. By the way, I think most of the formulas you need are inside the front cover of your book somewhere. And again, on the test, I'll give them to you if you need them. Okay? All right, but anyway. Okay, so once we come up with that equation, what's the next step, guys? What do I do now? What do I do to that equation? I differentiate it with respect to what? T, so I can get the rates in there. Are you with me? So watch how that goes. What's the derivative of V? Well, it's 1, but then I got to put a what? dV over dt. You already know why, right? Okay, over here, to differentiate that, don't I just bring down the 3 and subtract 1 from the exponent, right? And then I got to put a what? dr over dt. So again, what I did is I differentiated both sides with respect to t. Don't forget the dr dt. Is that clear? Because you're differentiating with respect to t, not r. If you're differentiating with respect to r, you wouldn't need the dr dt, would you? Is that clear? Right? Okay. So that's the tricky part. All right, and then I just simplified it. Those 3's cancel, and now I'm here. Okay. All right, so now at this point, what are you trying to find, guys? You're trying to find what? And again, by the way, I just recopied it down there. What are you trying to find now? You're trying to find what? What are you trying to find here? dr dt. So leave that alone. Okay, but you're trying to find dr dt at the moment in time when r is 20. So it's okay at this point to go ahead and put in that 20 for r. And so that's the mistake you're going to make. You're going to put that 20 in at the beginning. And as soon as you do that, it's going to be incorrect from that point forward. You cannot put in that r until after you've differentiated. Why? Because r is changing, isn't it? Isn't the radius changing as that balloon is inflated? Isn't r changing? Okay, so you're not allowed to put in that 20 for r until the very end, until after you've differentiated. Is that clear? Okay. And so from there, what else did I know? I was given dV dt, so I put that in. And so once I put in the 100 there, and then once I put in the 20 for r, I just divide both sides by that. And that takes me to there. Simplify to that. It simplifies again to that. And by the way, notice how I stuck the units on my answer. Where in the world did I get those units from? Well, this is a what? This is a change in r. So what would be the units on r in this case? Centimeters. Over change in time. So what would be the units on time here? Seconds. Okay? Everybody with me on that? And by the way, I think it'll be more meaningful if you change it to a decimal. And so if you do that, what do you get, guys? That. So again, what that means is, as that balloon is inflated, at the moment in time when the radius is exactly 20 centimeters, if you could put a radar gun on the radius, you would see that the radius is increasing at a rate of what? 0.0198 what? Centimeters per second. Is that clear? Yes? All right, what is the meaning of the fact that it turned out to be a positive rate of change instead of a negative answer? That means r is what? Increasing at that moment in time, which it clearly is, right? Okay, so pay attention to all the details. Make sure you understand where everything's coming from. Okay, good. All right, now, you guys, I got to warn you about something. In that first example, again, it told you that the volume is increasing at that rate. But again, let's look at an example where maybe it doesn't. So suppose in another example it gives you a rate of change like that, and it doesn't tell you what that is. How are you going to figure out what that is? By looking at the what? The units. What is feet squared? That's a unit of area, isn't it? Isn't square feet a unit of area? And what is hours? That's a unit of time. So even if I don't tell you that that's the rate of change of the area, you should be able to just look at the units and tell me that that's dA over dt. Is that clear? Yes? Okay? That's important because they might not tell you flat out what that is. Okay, good. All right, next example. And by the way, I know I put one exactly like this on the test. I know I put one exactly like this on the test. Exactly. Okay? Now, I might change the numbers a little bit, right? Or the scenario slightly, but very similar or identical situations, I should say. Is that clear? Okay. So, here we go. All right, so again, the problems are going to look like this. They're not always going to give you a diagram. You're going to usually have to draw the diagram yourself. And you know, that's the key. Once you draw the diagram, I think things flow pretty well from there. Okay, so stay awake. Stay awake. Okay, here we go. All right, it says a 10-foot ladder rests along a vertical wall. And then it says if the bottom of the ladder is pulled away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So here's what I did. I drew a picture of the situation. Okay? So I drew the ladder leaning against the wall, and notice what I did. I put the 10 in right away. Why did I put the 10 right away instead of putting like a Z there? That's a constant. Is the length of the ladder going to change? No. So you can put that in right away. All right, so what's going to happen now? As you pull the bottom of the ladder away from the wall like that, what's going to happen? Well, obviously, the distance from here to here is going to change, isn't it? So they call that some variable. Call it anything you want. I called it x. Is that clear that that's going to be a variable? That distance is going to change? So I have to label that with a variable? What else is going to change? Well, what's going to happen is the top of the ladder is going to do what? It's going to slide down the wall, isn't it? And so the distance from there to there is also going to change, isn't it? Yes? And so you got to give that some variable name. Call it y, call it h, call it anything you want. Just call it a variable. Is that clear? Yes? Okay? All right. And obviously that all three of those things form a right angle, don't they there? A right triangle? Okay, so now what are we given, guys? What is this 1 foot per second? What is that? What is that? That's how fast what? That's how fast the ladder is being pulled away from the wall. So isn't that the rate at which x is going to change? Yeah. And so I put that 1 there as what? dx dt. Why is it positive 1? Because x is increasing as you pull the ladder away. Is that clear? If x was decreasing, I would have stuck a negative on that 1, wouldn't I? Are you following me back there, guys? Okay? All right. What are you trying to find? Well, it says find how fast the top of the ladder is sliding down. So wouldn't that be how fast y is going to change? And so I'm trying to find dy dt. Okay? When? When the ladder is what? 6 feet from the wall. In other words, I'm going to find dy dt at the moment in time when x is what? 6. Are you clear on that? Are you clear on that? All right, now watch, because this is a mistake you're going to make. Everybody look up here. This is a mistake you're going to make if you're not careful. Some of you are going to say, oh, x is 6. I'm going to put a 6 there. No, no, no. Don't do it. Because x is changing, isn't it? You can only put the 6 in when? After you've set up the equation and you've differentiated. Then you can put the 6 in at that point. Is that clear? Don't make that mistake. That's the #1 mistake you're going to make right there. Don't do it. Right? So again, if you get this problem wrong on the test, chances are that's what you did. And guess what? One of the wrong answers is going to be what you get if you put the 6 in too soon. Right? So you're going to think you got the right answer, but Got it? Be careful. Okay? Be careful. All right. All right, so what do I do now? Okay, so I've got the diagram. I wrote down what I'm given. I wrote down what I'm trying to find. What comes next? You got to come up with a what? An equation that has what in it? X, Y, and hopefully the 10 as well, yes? And so, Haiji, what equation in this scenario would relate X, Y, and 10? What equation are you going to use? Just look at it. It's a right triangle involving the 3 sides. So what are you going to use? Pythagorean theorem. Everybody agree that's the equation you're going to use? Yes? Okay, so I wrote down what then? X squared plus Y squared equals 10 squared. Are you following me? Okay, then what comes next? After you write the equation, what do you do next? Differentiate both sides with respect to t, so you can get those rates in there, yes? So that's what I did. Quickly, what's the derivative of that? Quick. 2x, and I got to put a what? dx dt. Plus, what's the derivative of y squared? 2y, and I got to put a what? Times dy dt. And then equals, what's the derivative of 10 squared? Be careful. 0. Isn't 10 squared a number or constant? What's the derivative of constant? 0. That's another mistake you're going to make. You're going to put that 100 there, and then it's going to be wrong, isn't it? Don't make that mistake. Okay, now watch what happens, because we're going to get stuck here in a minute. And then I got to show you how to get unstuck. Are you ready? Okay, isn't this the point where we start putting in what we know and hopefully solve for what we're looking for? Okay, so you're trying to find dy dt, so you leave dy dt alone. Okay. You know dx dt, so you can put in a 1 there. So I replace dx dt with 1. Is everybody clear on that? Yes? And you're trying to find dy dt at the moment in time when x is 6. So this is the point where it's okay to put in the 6 for x. So replace x with what? 6. Are you following me? Okay, what am I missing though? What am I missing here? I'm missing what? I kind of messed it up, but what am I missing here? I'm missing the y value. So I'm stuck, aren't I? I'm not going to be able to finish it without that y value. How am I going to get unstuck? Eric, please, head up. How am I going to get unstuck? How am I going to get unstuck here? Well, let's think about it. Aren't I at the moment in time where I'm trying to find dy dt, you know, at the moment in time when x is 6? So is it okay now to put in a 6 there now? Yes, it is. So what I'm going to do is I'm going to momentarily freeze my situation here at the moment in time when x is 6. And by doing that, won't I now be able to find y at that moment in time, which is what I need to finish the problem at that moment in time? Yes? So what I did is I wrote what? Y squared plus 6 squared equals what? 10 squared. And then just solve that for y, and you get what? 8. So now I'm okay to go ahead and fill in my blank there with a what? With an 8. Are you following me here, guys? And then simplify this. This turns into 12. This turns into 16 dy dt. Then subtract the 12 from both sides and divide both sides by 16. And that simplifies to 3/4, negative 3/4. And where did I get the units on my answer, guys? Where did I get those from? Well, what's the units on y? Feet. What's the units on t? Seconds. And so you see how I got the units feet per second in my answer? By the way, notice how my answer turned out negative. Does that make sense? Yeah, why? Because y is decreasing as that water slides down the wall. So you would expect to get a negative answer. If you didn't, you did something wrong. Is that clear? So make sure you look for that kind of stuff. Okay? Good so far? Not too bad, right? Well, it's going to get harder a little bit. Okay, so let's look at another problem. Ready? After this one, I'm going to let you try one on your own. But again, this one is definitely trickier than example 2. So everybody follow along. Are you ready? Okay, we got that same scenario at the beginning of the hour. Remember when I talked about a cone filled with water leaking out? Do you remember that? Okay, so what did we say in that problem? As time changes, doesn't the water leak out, causing R to change and causing H to change and causing the volume of the water to change, right? So you agree R, H, and V are all variables here? Yes? John, is that making sense here, that V, R, and H are all variables here? Okay. All right, so let me read the problem. Okay, so water is leaking from the bottom of the tank. Okay, and by the way, the tank has a height of what? 4. So in my diagram, the distance from here to here will always be 4, won't it? Okay, what else does it say? The diameter of at the top is what? 4. So if this is 4 from here to here, what is the radius from here to here? 2. Somebody agree where everybody see where I got that 2 from there? Okay? Are we good? All right. All right, so let me continue reading. It says the water is leaking out at a rate of this. Now again, I didn't tell you what that is. So how do I know what that is right there? How do I know what the 2 cubic meter per minute is? Well, you look at the units. What is meters cubed a unit of? Volume. What is minutes a unit of? time. So even though they don't tell you that's the rate of change of the volume, can't you figure that out from the units? So isn't dV dt 2 here? But wait, why did I put a negative 2 instead of just 2? Because V is decreasing. So you better put a negative on the rate of change. Is that clear? See how there wasn't a 2 in the given information, but I stuck a 2 in there right away? I'm sorry, not the 2, the negative, I should say. See, there's no negative there, but I stuck the negative in right at the beginning because V is decreasing over time. Okay? With me? With me? Okay. All right. All right, now, continue reading. What does it say? It says find what? The rate at which what? The water level is falling when the water level is 3 meters. And so the way I drew it, what's my water level? H. So I'm trying to find dH dt at the moment in time when what? When the water level H is 3. Are you following me on that? You see how I wrote down what I was given and what I'm trying to find? You have to do that. If you don't do that, you're never going to be able to get the next step and finish the problem. So always write down what you're given. Always write down what you're trying to find and when, if they give you that information. Okay, so clearly what do we need here? We need a volume formula for a cone that relates V and what? H. Well, the only volume formula I know for a cone is this. Everybody agree? That's the one I put up there at the beginning of the hour. Do you remember that one? The volume of a cone is 1/3 pi r squared h. Okay. Now watch what happens. I'm not going to do this again, but do you remember when I took the derivative at the beginning of the hour, right? Remember that? And over here I used the product rule and I came up with this at the beginning of the hour. Do you remember that? I'm not going to go through it again, but there it is. Okay, you already remembered me doing that at the beginning of the hour? I used the product rule here and differentiated and went through all that. Okay, and I came up with that. All right, now there's a problem here. There's a major problem here. What is it? What's the problem with that equation? Well, look, it's okay for your equation to have V in it, because I know dV dt. It's okay for your equation to have H in it, because I'm trying to find dH dt when H is 3. What's not okay to have? R. Because by leaving R in there and differentiating, didn't I get a dr dt? Do I know what dr dt is? No. Am I trying to find dr dt? No. So it can't be there. That's a problem, isn't it? So this isn't going to work. It's not going to work because it has a dr dt in it. I'll get stuck if I try and use that. You see how I'm stuck? All right, now you got to know how to get unstuck, and that's the tricky part. How do I get unstuck? In other words, how do I get rid of that R at the beginning before I even differentiate? Well, let me talk about it. Everybody agree that that R cannot be there when I differentiate, because if I leave it there when I differentiate, I'm going to have a dr dt, and I don't know what dr dt is. I'm going to be stuck. You see why that's a problem? Okay, so how am I going to get rid of that R? Well, you're going to have to get creative, and let me show you what I mean by that. Ready? Let's study my diagram for a minute. If you study your diagram for a minute and look at this 2 and everything else, and the 4 and the R and the H, isn't it H from here to here? Okay, and isn't it R from here to here? Take a look at it. Don't I have similar triangles being formed there? That's a right angle, that's a right angle. So because the one little triangle is inside the big triangle and they're both right triangles, doesn't that make those similar triangles? And what did you learn back in geometry about similar triangles? You can write proportions involving the lengths of the corresponding sides, can't you? So there's lots of ways you can write those proportions, but here's one way. Can't you say that that R to that H equals that R to that H? Can't you? Can't you? So can't you say R is to H is 2 is to 4? Can't you? Okay, and by the way, I can rewrite that as what? I can just rewrite that as what? R equals what? 1/2 H. Are you following me on that? And so now what I'm going to do is I'm going to use that, the fact that R is equal to 1/2 H, I'm going to substitute it in here. So what am I going to replace R with? 1/2 H. And please simplify this before you do anything else. So if I square that, don't I get 1/4 h squared? Yes? Following me? And then by the way, what's all that turn into? All that turns into what? Pi over 12? And I can combine those into what? H cubed. See what I have now? See how I've eliminated r? So I've eliminated my problem. You agree I've eliminated my problem by eliminating r altogether from my volume formula? Okay? And now I'm okay to go ahead and differentiate. Because now if I differentiate both sides, I'll be good. Yes? Okay, so quick. Here we go. So what's the derivative of that? 1, but then I got to put a what? I'm differentiating with respect to t, so I got to put a what? dv over dt, right? By the chain rule. Okay, to differentiate that, don't I just bring down the 3 and subtract 1 from the exponent? And then I got to put a what? dh over dt. Is everybody with me on this? Okay? Okay. So at that point, what are we trying to solve for again? We're trying to find what? Trying to find dh dt, so you can leave that alone. Okay, but if you're going to be able to find dh dt, then you better have all other missing quantities now. So I'm trying to find dh dt at the moment in time when h is what? 3. So is it okay if I put a 3 in there now? And don't I know dv dt? What was that? -2. So from here, you just have to solve for dh dt now. Okay, so it's just algebra from here. Is that clear? Yes? So just simplify all this and divide both sides by that and simplify, and you end up with your answer, which is what? You end up with what? Yeah, -8 over 9 pi. And again, where did I get those units on my answer from? Well, h would be in what? Meters, and t would be in what? Minutes. So that's the rate at which h is changing when, at the moment in time when h hits what? 3 meters? By the way, does it make sense that I ended up with a negative rate of change for h? Yeah, why? Because h is what? Decreasing as that water drains out, isn't it? So it makes sense that I get a negative dh dt for my answer. If you don't, you did something wrong, right? Okay? All right, so I'd like you to now go ahead and try example 4 on your own. Be careful. Draw a diagram, guys. It's a cylinder, guys. Careful, not a cone. Don't get those two mixed up. It's a cylinder, not a cone. And put variables on things that will change, and put constants on things that won't change. That's what you want to do after you draw the diagram. You guys need the volume formula for a cylinder, or do you know it? What is it? Anybody know what it is? V equals pi r squared h. So it's the same thing as a cone without the 1/3, right? Got it? So V is pi r squared h. Given, write down what you're trying to find. Okay? Write down what rates you are given, what rates you are trying to find. And then go from there. And differentiate your equation. So, here we go, guys. Okay, let's look at example 4. Ready? There it is. Okay, so the first thing I'm going to do is draw a diagram. Okay, you got a cylinder tank, right? And it's being filled, or is it draining out? Which one? It's being filled. So water's going in, right? And clearly the water itself is also going to form a cylinder, isn't it? Okay. And so what are you given? Well, you're given this, and it doesn't tell you what that is. So you're going to have to look at the units to figure out what that is. 5 cubic inches per second. What is inches cubed a unit of? Volume. What is seconds a unit of? Time. So they're definitely giving you the fact that dV over dt is 5. Positive or negative? Positive. How do you know? Because water's going in at that rate, so clearly the volume's increasing, so it would have a positive rate of change, wouldn't it? Okay. What are you trying to find, guys? Well, it says to find the rate at which the what? The water level is rising. So, that's up to you what you want to call that. I'll just call it H. Call it anything you want. Okay, so I want to find dH dt, right? At the moment in time when what? When H equals what? 8. Is that clear, guys? Yes or no? Okay. And so, by the way, then, so what do we do next? Well, basically, you want to write an equation that has V and H in it for a what? For a cylinder. Well, what's the volume formula? The only volume formula you know for a cylinder. What is it? V is pi r squared H. Agreed? Okay. Now, we kind of have a similar problem to the last one where I can't have R in there, can I? When I differentiate, I cannot have R in there because I don't know what dr dt is. Okay, but hold on. Yeah, okay, I'm getting there. But let's look at the radius for a minute. What is the radius? It tells you it's what? Well, it has a diameter of 6, so clearly the radius is what? 3. It's 3 there and it's 3 there. Isn't it always going to be 3? And so R is not a variable here, is it? Like it was on a cone. On a cone, R changes. On a cylinder in this problem, it doesn't change. So guess what I can do right at the beginning before I differentiate? I can put in a 3 there before I do anything. If R was changing, I could not put in that 3 until the end. Is that clear? Yes? Until after I differentiate, but in this case, R is a constant, so I can put that in right at the beginning. Okay, and by the way, that turns into this, doesn't it? All right. So now are we okay to go ahead and differentiate this equation with respect to t and to get the rates going? Yes? Okay, so here we go. What's the derivative of v, guys? Well, 1, but then I got to put a what? dv over dt. What's the derivative of that with respect to t? Well, if that was like 6h, for example, what would be the derivative of 6h? 6. Well, so in this case, what's the derivative of 9 pi h? 9 pi, but you got to put a what? dh dt, because again, we're differentiating in respect to t, not h. If we were differentiating in respect to h, we wouldn't need that, would we? No. Okay. All right, so just simplify this. And by the way, now we can start putting in what we know and solve for what we're looking for. We're trying to find dH dt, aren't we? So you can leave that alone. Just leave that the way it is. You're solving for that in a minute. And you're trying to, so again, you're trying to find dH dt, so leave that alone. Do I know dV dt? Yeah. That was given to be what? 5. And so you can go ahead and just solve now by dividing both sides by 9 pi, right? And so you get dH dt is equal to this. Now, what are the units? Well, what would be the units on h? Inches, is that right? And what are the units on t? Seconds. So dH dt is changing at that rate. And by the way, what does it mean that it turned out to be a positive rate? That means h is what? Increasing, which it is, isn't it? By the way, one thing I got to point out here. Please don't go writing that like this. Don't get sloppy and write it like that, because that looks like it's 5/9 pi. Is that the same thing? No. So if you write it like that, it looks like the pi is off to the side, which actually means it's in the numerator. So please don't get sloppy. Make sure I see that the pi is in the bottom, which it is on this problem, isn't it? Yeah. Yes? Okay, be careful not to make that mistake. Okay, just a couple more things I got to point out, and we'll finish up. Okay? Did you hear my voice on the speaker? Was it coming through just now? Okay, because I forgot to put this on. I mean, it was sitting close to me. I hope it worked. You don't think it was? Okay. Anyway. Let's look at, yeah, I don't think it was working either. All right. I'll check it. Remind me to check it so I know whether I need to record third hour. Okay. So here we go. We got a cylinder again. Okay, but this time it's a totally different situation. This is not a tank. This is an ice sculpture. Okay, and you've all seen like ice cubes melt, right? Don't they melt uniformly? They kind of keep the same shape. They just kind of get smaller, right? And so if that thing's melting, okay, and you want to talk about, you know, R and H and all of that, right? And V. As that thing melts, what's changing? Everything's changing. V's changing, H is changing, R is changing. Okay? And so when you write the equation here, okay, well, again, it's V equals pi R squared H. You're not going to be able to put in a constant for R like you did on the last problem, are you? No. Even if you knew what it was at the start, you could not put it in, could you? No. Because as that ice sculpture melts, everything's changing. And so I'm going to go ahead and now differentiate everything with respect to t. Ready? Here we go. What's the derivative of that? Well, 1, right? And derivative of v is just 1. And I got to put a what? dv over dt. And here, don't I need to use the product rule? Because r and h are both going to be variables throughout. Yes? And so I have to use the product rule. So here we go. Derivative of the first, which is 2 pi r to the first. And don't I need to put a dr dt? Okay, so that's the derivative of the first times the second plus the first. And now times the derivative of the second. What's the derivative of h? Well yeah, 1, and then you got to put a dh dt, right? All right, and then you can just clean it up and go from there. Is that clear? Okay? All right. Let's look at example 6. All right, so this time, let me draw it a little bit bigger. And the water drips out into here, right? So you got the water, or the oil starting out. And I'll call this H2 and I'll call this R2. And I call this what? Well, the water's going to be in here, right? So I'll call this what? R1 and H1? Yes? Okay. Okay. And so what's happening here is the oil's starting out up here in the shape of a cone, and it's leaking out into the cylinder, right? And so up here the water forms a cone, down here the water forms a cylinder, right? Okay, and so it says to write a formula for the total volume of oil and then differentiate to get a related rate equation for everything. Are you ready? Here we go. So what is the total volume V here, guys? What is it? Well, yeah, you got the volume up here. What's the volume up there? 1/3 pi r squared h. And by the way, make it R1 and H1. Is that clear? Yes? Plus, you're going to have the oil down here, which is what? What's the formula for that oil? Pi r squared h. And again, make it R2 and H2. Is that clear? Yes? Everybody agree that's a total volume V between the two? All right. And now I'm ready to differentiate. Now be careful. Are all these variables in this problem? Let's talk about each thing and tell me if it's a variable or a constant. Is R1, again, as this water drains out into here, is R1 going to be a constant or a variable? Variable. What about H1? Constant or variable? Variable. What about R2? Constant. So I'm going to circle that. That's going to be a constant. What about H2? Variable. Okay, now the tricky one. What about V? Very good. Everybody agree V is a constant? You got some up here and some down here, don't you? But the amount never changes, does it? Does it? No. The total amount between the two is never going to change, is it? So do you agree that V is a constant? Yes? And do you agree that R2 is a constant, but all the other things are variables? So watch how this is going to work now when I differentiate. Be careful. Ready? I'm going to now differentiate both sides with respect to t. Here it goes. What's the derivative of v? Very good. I thought you were going to tell me dv dt. It's 0, isn't it? Right? And by the way, even if you did put dv dt there, what is dv dt? 0. Right? Got it? The volume's not changing, right? At all, is it? So dv dt is 0, right? Okay. All right, now what about here? Again, R1 and H1 are both variables, so aren't I going to have to use the product rule there? Aren't I? Yes? So here it goes. So what's the derivative of this? Well, I bring down the 2, multiply it out front, and then subtract 1 from the exponent, right? And then I got to put a what? dr dt? Yes, dr1 dt. Okay, so that's the derivative of the first, times the second, which is just H1, plus the first, which is just this, and now times the derivative of the second. What's the derivative of H1? Well, 1, and then I got to put a what? dH1 over dt, okay? And then plus. If R is a constant, guys, if R2 is a constant, isn't this whole thing just going to be some number? And so you can kind of think of that like as maybe like 7h. What would be the derivative of 7h? 7. So what's the derivative of all that h? Pi r2 squared. But then I got to put a what? dh2 over dt. Everybody agree that's what you would get? Yes? Okay? Can you handle that? It's not going to get any harder than that, I don't think. And you can just clean it up and do whatever you got to do to answer some questions, right? Okay? Yes.
Isn't the radius 2 not changing over time?
It's not. And so you treat that like a number, like I said. So pretend like that was 7h2. What would be the derivative of 7h2? 7, right? And then you'd have to put dh dt after that, right? So that just treat that like a whole number, like a constant, right? Got it? Because R2 is just a constant. It's not a variable. Okay, so that's why I didn't need to use the product rule there, did I? I didn't need to, right? Because R2 was a constant, not a variable. That's why I didn't use the product rule there. Whereas here, those are both variables, which is why I had to use the product rule to get all of that when I took the derivative of this. Does that make sense? Okay, all right. Now look, they're going to have all kinds of different shaped tanks on the homework tonight and on the AP exam. Who knows what the tanks are going to look like? So we need to talk about how we use geometry to come up with the volume formulas in case they don't give them to you. Okay? And so let me start out with a cylinder. Okay? We already said that the volume is what? What's the volume of a cylinder? Pi what? R squared h. Now hold on a minute. Let's talk about where that formula came from. Where did this come from? The area of the what? Of the circle. And by the way, don't you have the same shape on both ends? That makes this a what? Prism. So technically a cylinder is a circular prism, isn't it? Again, a prism is when you have the same shape on each end. Same size and same shape, yes? So technically you can think of this as a circular prism. And so how did we find the volume? You take the area of the end, right, or base, whatever you want to call it, and multiply by the height or thickness between the bases? Isn't that basically where that formula comes from? Okay, well, if that's the case, then isn't this a prism here, right here? What kind of prism is it? Rectangular prism, because you have a rectangle on this end and then the same rectangular shape on that end, yes? And so wouldn't you take the area of that and multiply by the height or thickness, which in this case I told you is 6? So isn't that how you could get the volume formula for that? Yes?
Yeah.
What type of prism is this? It's a triangular prism. You have the same triangle on both ends. And so to find the volume of that, wouldn't you take the area of one of the ends and multiply by the thickness between the ends? Yes? You following me? What type of a prism is this? Trapezoidal prism, because you have the same trapezoid on each end. And so wouldn't you take the area of one of those trapezoidal ends and multiply by the height or thickness between them? So you see how it's always the same no matter what if you got a prism? Same approach at least? Yes? All right, here's what they did one year on the AP exam. They had a cylinder. They called this H, and they said the area of the circular base was maybe like, I don't know, 16 square inches or something. And so what would you write for the volume of that? V equals 16H. So you see why you got to know this concept in case they throw something like that at you? Yes? Got it? Yeah, they expect you to be experts in all your previous subjects. And you should be. All right. But anyway. All right, so there it is, guys. I'm done. You guys, look, take a break, but you got a lot of time. I don't want you to waste it. I mean, these problems look easy when I do them, but you're going to run into problems when you start doing these. So take a little break for about 3-4 minutes, and then I want you starting and working on this the rest of the hour, okay? And ask me for help if you need it.